Hello and welcome to episode 223 of Quarkus Insights. This is the episode that we were supposed to have last week, but we got taken out by the AWS outage, so we're having it this week instead. It's the evolution of Java code execution with Ben Evans. And of course, even this week we have some mini challenges, don't we? Because for part of the world, this is not at the usual time. And for part of the world, this is at the usual time.
I'm trying to figure out which part is the right part and which part
yeah,
is the wrong part.
yeah. And it wasn't the way around that I thought it was going to be. So
Yeah, we ran into that ourselves because you guys are in Europe and I'm in the US. So I'm pinging Holly on the side, like, are you coming? Like, coming where? It's an hour from now. But then, Ben, you're in the same time zone and you were here. So we, amongst ourselves, trying to figure out what's the right time. Is it now or is it an hour from now?
Yeah. And I think it's because Ben doesn't have the habit, whereas I have the habit and I know that it's at 2 UK time. And I also know that in this 2-week period, and Ben, you said you called it Broken Week, which I thought was such a good name.
Yeah.
And in this 2-week period, I know it's wrong, but usually what we do is we anchor the invitation to the European time zones. And so it stays at the same time for European time zones. But this time we anchored it to the US time zones. So it moved for the European time zones. And some years as well, what we do is we split the difference. So part of it anchors to the US time zone and part of it anchors to the European time zone to make sure that no matter what, nothing functions.
Yeah, but at the end of the day, time zones is still one of the hardest problems in computer science, right?
Yeah.
Yeah.
That naming things.
If you draw a straight line through, I think it's Utah, the American state of Utah, and if you strictly follow the rules about time zones, you can change your clocks 9 times without ever leaving Utah.
Really?
Because you have things like Indian reservations, and in the Indian reservations, they can choose, because they have that status, whether or not to apply daylight savings or not. So, in fact, there are 2 different Indian tribes, one of which does use daylight savings times and one of which doesn't. But they have enclaves inside each other's territory. So you can draw a specific straight line. And yeah, 9 times it's flying over Utah.
And then you get to Arizona and then parts of it do change and Arizona doesn't change. And there's that like line on the Hoover Dam in Arizona or Nevada where it's like, depending on which time of year, they're either at the same time or they're at different times because one changes and one doesn't.
Cool.
They should just abolish. We have this conversation every year. Like, why do we still do this madness?
Yeah, I did a project a while ago. It was sort of an e-health project. So it was sort of, using sensors to track the elderly. And it creates like really fundamental problems that you sort of can't, like, first of all, there's the I didn't think about it programming error, but then there's the I did think about it programming error, and I still can't figure out what the right behavior is. Like if you're tracking the vitals over a 24-hour period, but 24 hours is either 23 hours or 25 hours, like do you track some of yesterday's vitals and today, and then that seems wrong, or do you like have a 23-hour day, which seems worse if you're tracking vitals, because then, so yeah, chaos.
And you got to throw a leap year and a 53rd week into everything, and
yeah, computers are hard. I think they were a mistake.
We should just go back to punch cards, right?
Yeah.
Anyway.
Yeah.
What are we going to talk about, Ben? You're here. You're our guest.
Yeah. So I was going to. I'm just waiting for Holly to stop sneezing.
Yeah. You okay, Holly?
Yeah.
Yep. Sorry, I was about to say something and then I realized I had to mute urgently because I was about to like make cough noises and deafen everybody. Sorry. Carry on.
I was afraid someone's gonna have to come over and do the Heimlich maneuver or something.
Yeah. So today we're talking about code execution. So basically, this is actually one of those things which is kind of a really old topic, but it's also sort of new again, because Java has had this sort of standard execution model right since the earliest days. So some of what we're going to talk about today is just like the earliest design decisions that went into the way that Java is. So you might think, well, then, what are we actually going to talk about then? Because surely all of this is done and settled and gone. But of course, with technologies like Quarkus, sometimes you get an opportunity to revisit that. And so we're going to talk about how this ancient subject is suddenly coming back again, is suddenly interesting again, and how in some ways Quarkus predicted the future, but also is helping to dovetail and to even to drive some of the future that's coming for us. So that's basically what I wanted to talk about. So maybe we could start and just lay out what the classic model of Java execution looks like. So if we can, perfect. So this is one of my classic pictures. This shows the standard way that we get a Java application to run. We start with some source code, which is human readable. We put it through Javac, which is probably being driven by Maven or whatever, and we end up with a class file and a set of bytecode. So from that, we actually need to get that into an executable form because, as I hope everyone knows, bytecode is machine independent. It's not human readable. It's very much a binary format. But what people may not know is it's not actually very similar to real machine code at all. The best way to think about it is if you've done a compilers course at university, I would say that a class file is kind of like an intermediate representation. It's not really an abstract syntax tree, although it's related, but it's an intermediate representation. It's the output of the front half of a compiler, if you know what those types of bits of jargon mean. Okay, if you don't worry. It's a kind of intermediate thing that's produced by Javac. And it comes out in the class file format, and that's what gets ingested into a VM. The JVM has to have class files. You cannot get code into a JVM by any other mechanism. Class loading is the only thing it provides you with. And there's a couple of reasons for that, but one of the main ones is because it provides you with this sort of lovely pinch point for the classes to come in. If there's only one way in, that's the part you have to secure. That's, it allows you to concentrate your efforts on ensuring that nothing malicious or nothing bad or anything with exploits in it can get past that choke point. So that's a very deliberate design choice, is to do everything via class loading and to make everything, every program that runs within Java a class is something which goes back to the very earliest days. Okay, so it comes in, you do the verification and so forth, and then you chop up the class you've loaded into methods and get it set up as a type known to the VM, and then you feed it into the interpreter. So now we're doing bytecode interpretation. Hotspot actually has two separate interpreters. I don't know if people know that, but there are actually two different ones. There's the standard one, which is the template interpreter, which is what you get by default. And there's also what's called Zero. And the reason it's called Zero is because it's not implemented in assembly like the usual one is, but it's written in C++. And it is literally just a big switch statement inside a while loop. So it's a very traditional interpreter. Why am I mentioning it? Because it's actually turning out to be important again. Because in terms of evolving the execution model, one of the things you might not know is that up until now, it's been essentially impossible to run Java on iOS because Apple have restrictions about the use of dynamic code and especially things like JIT compilers. But with the Zero interpreter, people are now discovering that they can write in such a way that OpenJDK is now able to run on iOS. So it's a small example of how the execution model is changing, but it also speaks to the flexibility that Hotspot has. Anyway, so there are two interpreters. For the purposes of this discussion, it doesn't actually matter which one we're using, but it executes bytecode, and Hotspot, this is where its name comes from. This is where the original, some of the super smart, some of the groundbreaking stuff that was groundbreaking, I guess, 20 years ago, but is now kind of mainstream. This is where some of it comes in. One of the principles in Java is it's based on a design bet that there is runtime information about your program which you can exploit. Okay, so when a Java program is running, there are parts of the JVM itself that are watching what's going on. They're collecting bits of data, they're gathering statistics, and that influences and affects the behavior of the Java runtime itself. In this case, it's collecting statistics on which methods are getting executed, where the hot spots of code execution actually are, which is where the name comes from. So once it's determined those, then a separate subsystem which runs on separate threads. So these are threads that are owned by the VM. They're not owned by the Java programmer, and they are able to spot where these methods are and to take them and compile them into machine code. So this is the red box on the diagram here. We have the profiler, which is counting what's getting executed, and then we have the emitter, which generates machine code, which is semantically equivalent to the bytecodes that were previously there. That emitter then puts things into the code cache, and this is where a lot of the optimization is done. Javac as a source code compiler does no optimization basically, because the design philosophy here is that you keep the bytecode simple and kind of dumb, because what you want is the JIT compiler to have an easy life. The JIT compiler has got access to all of this lovely runtime information, which is really powerful and can be used for making incredible optimization decisions. So you want not to get in its way. You want to give it an as easy job as possible. So you can kind of think of the class file format and of the output of Javac as being an input format for the JIT compiler.
And this kind of goes towards the whole startup versus warm up time, right? Is what you're talking about.
Absolutely. So this is the point. Eric's absolutely right, because all of this is going to take some time, right? You don't really know where the hotspots are until you start running the program. And also, Holly.
Oh yeah, no, I was just going to say it's also exactly like what you would do with people, right? So if you were a person and you were writing it by hand, you would say premature optimization is the root of all evil. It's going to take you a lot of developer time to optimize it, and also your colleagues are going to have to read your code, and don't make your colleagues read your heavily optimized code unless there's actually a benefit in it.
Yeah.
So if you think of the JIT as a colleague, yeah.
Yeah, actually, I've never thought of that before. I like that. Yeah, I'll have to think about that. So yeah, and so of course all the other optimizations which happen here. So for example, one of the things the JIT compiler is going to do is it's going to do method inlining, and method inlining turns out to be one of the first optimizations that the JIT does, because it brings more code into the context of what the JIT compiler is looking at, and that means you can sometimes do other optimizations that you wouldn't have thought of. You can suddenly realize, oh yeah, actually that bit of code's dead, or now that I've collapsed and telescoped these three methods into one, I can see that value doesn't escape. So I can do escape analysis on it, right? So these types of optimizations, which are fed in to the it by inlining. So all of this is taking a little bit of time. We need to identify the methods, we need to warm them up, and then of course we actually have to do the work of compiling them. Hopefully that's not too much work, but sometimes it is. And so as Eric points out, this leads us to warm up. And this is one of the classical pieces of the design of Java, which I think has been a problem, as we've transitioned into the world of the cloud, because Java's original design assumes long-running processes on large bare metal servers. So part of what we're going to be talking about today is how do we rethink those design assumptions? How do we go at it afresh and find a different way to handle that? Because the warm-up times can be considerable. If I'm writing a trading system that's going to be up for all week, I'm going to switch it on Monday morning and I'm going to close it down when it's time to go home on Friday evening. Yeah, sure, a little bit of warm-ups, and we're talking seconds, maybe a minute. That's okay. That's not really a problem. But if I'm writing on the other extreme, an AWS Lambda, which is fire once and throw it away, well, that's a problem, because it's never really going to get out of warm-up. It's never going to get out of second gear. So the performance characteristics of a very long-running system, where the cost can be, we say, amortized, it can be basically averaged out and say, okay, well, we got to pay the startup and the compilation costs, but we only pay that once, and we've got all this lovely fast runtime that we get because of it. Shorter-lived processes do not have that opportunity to amortize, and that is what we see. So this is I think the start of where we want to think about how we've modernized things. Something else I wanted to say. So it's also probably worth just mentioning briefly how the heap layout works as well. So in general, Java's got a couple of areas of memory. Oh, actually, I should probably show this diagram first. There we go. This is a standard kind of Unix process layout. You have a stack and a heap, which are the light blue, and then the darker blue is the Java parts of that. So Java's just another process. It still obeys all the rules of Unix and Unix-like operating systems, just like everything else does, just like every other programming language. So that's the light blue stuff. Every process looks like that. And then we have the dark blue, which is the Java piece. So we can see, for example, that within our C heap, as we call it, we have a continuous block of memory, which is the Java heap. So when the Java process starts up, it says, right, between that address and that address, that's mine. I'm going to manage that. Everything inside there is my responsibility. The operating system can stay out. So that is that's also something people don't always realize. All of Java's garbage collection takes place in user space, with the exception of if you need to actually allocate a new physical page. Obviously, the operating system will have to give you to say, okay, well, that window of memory there is now backed by these physical bits of silicon memory on disk. That's an operating system task. But apart from that, everything else is done in user space.
Why is the heap triangular in that picture?
Oh, purely for visual effect. I mean, we have to remember this is a fiction, right? The address spaces are one-dimensional. So even the fact that I'm using a two-dimensional picture here is purely a visual aid for humans. It's not really. It's one-dimensional inside the computer. So
that would be a terrible picture.
Sure, but also, a heap is kind of triangular, isn't it? A heap of stuff. It's
Yeah, I see what you mean. Yeah. Yeah.
We could debate what actual shape that is. I think it's a trapezoid, right?
I think it is a trapezoid.
Yeah, I was being casual. But I guess it also sort of suggests like the size, doesn't it? Because it sort of foreshortens off into the distance because it's so huge.
Yeah. So basically this is it. You have Java stack frames inside your C stack frames, you have Java heap inside your C heap, and then in the C heap we have, if we zoom in on that a bit, we can see we've got the Java heap, we've got the meta space, which is where all the bytecode lives, and the class definitions. We've got the code cache, which is what the JIT compiler uses to store stuff, and then you have off heap memory. So this is a very traditional sort of runtime view of what's happening within a Java process. But if we think about how we might evolve this, there's a bunch of different things, and I think first of all it's worth laying out some of the rationale and some of the reasoning behind JIT, because sometimes people come with the argument that, well, can't we save the output of the JIT and then not have to rerun it next time? And sure, I mean it's an idea which has had a long history, and the answer turns out to be more complicated than you might expect.
I was just going to say we've got that leads us neatly into one of our comments, which is one solution that is worked on is Crack, although we still need to get the VM hot for the checkpoint. And I think you're about to give some commentary on the strengths and weaknesses of Crack as an approach.
Yeah, absolutely. We can talk about Crack. It's probably important because I think Crack will come in when we talk about Quarkus, because Crack needs to solve some of the same problems that we see in Quarkus. But just as a general piece of background, it's not just the code that's a problem, right? Because with something like Crack, we'll do a proper deep dive on it. But there are things like network sockets. There are other parts of the process which need to be frozen in order to be able to restore it. And the parts which are outside of the memory and the running state of the memory of the process are a complex issue. But even within the process itself, let's pretend that we just have a calculation engine, and all we're doing is we're saving the JIT compiled code. So this isn't an attempt like Crack is to take the entire state of the process, save it, and then restore it back to the same state. What we're thinking about here is, can we just save out the compiled machine code and reload it so we don't have to wait for the profiling and wait for the hotspot warm up next time? And the answer is yes, you can, but you need to be careful doing that. There are two separate JIT compilers in wide use within Hotspot. And it's worth knowing what they are and the difference between them. For people who've been using Java for a long time, you may know them as client and server. I'm probably showing my age here by using those words because they haven't been called that for quite some time. But their proper names are the C1 JIT compiler and the C2 JIT compiler. And they are very different beasts. C1 is a very quick and simple JIT compiler built with, I would say, very standard techniques. There's nothing really exciting in C1. It does simple optimizations where it can prove that the optimization is correct. C2, on the other hand, which came out of the work of people like Cliff Click some time ago, but it was quite challenging and quite groundbreaking when it first came out, is very different. C2's real power comes from what are called speculative optimizations. Okay. Now, remember earlier where I said that the JIT compiler will only produce semantically equivalent machine code. So you might think, okay, well then how does that work? Is it speculating, or is it producing things which are definitely semantically equivalent? And the answer is, it produces speculative code, but it always includes an assumption check. And if the assumption is ever invalidated, before it executes any incorrect code, it dumps and switches back to interpreted mode. So you always have protection. You're never going to do anything semantically invalid.
So it's not like it speculates that you want to transfer £1,000 to this bank account and then just doesn't check the assumption.
Right. The assumptions are always there. So to give you an example of what a speculative optimization might look like, something like 95% of standard Java calls, i.e. invoke virtual, always have the same type at that location. So if you're basically your Java source code where you make a call to a virtual method, or instance methods, I think is slightly less, but for a standard virtual method, I think in general, and these are very high level hand wavy numbers, 95% of the time, it's always the same type, which means it's always the same call. Okay, because if it was a different type, you would look up in the virtual table and go to potentially a different method, because that's how virtual dispatch works. That's the point of it. But 95% of the time, it's always the same. And that, I mean, across a whole program or across a whole code base. I don't mean at a particular site in general. So what that means is if you can include a speculative optimization, which says, yeah, we've been through here 1,000 times or 10,000 times. It's always that. Well, I think it will always be that type. You can include a check to say, is it really that type? And then if the answer is yes, you can do a direct branch. That optimization.
Check in my cache, and if it's in the cache, then return the cache. Otherwise, drop it from the cache, kind of thing that we always mix in with our programs.
Absolutely, yeah. And in fact, there is actually a refinement of it which does exactly that. You can do a trick where you can do two. You can have two possibilities at the same call site, and it uses exactly that technique. So that optimization it's brilliant. But there's two things about it that I want to point out. First of all, because it's a check of, and what you actually check is the pointer. You say is the class type of this object the same as the one that I've got cached, and that's one comparison. So it's one machine operation, which is obviously more or less free. It will probably hide in a pipeline bubble, and then you have a direct branch, because if it's correct, branch to the method definition. That optimization is only possible at runtime because you cannot predict it from static data. So an ahead of time compiler cannot do it because you require runtime information. And secondly, it gets rid of the vtable lookup completely. So it's faster than C++. C++'s vtables always require a double pointer in direction to do that hop, but we can do it with a direct call. So this is another point about execution in general that I want to make, is that sometimes people think about Java where you have all this overhead. You have a garbage collector and you have object headers which are always present on every Java object. Well, yes, you do. But sometimes having a structure and a specific layout enables you to make optimizations which are not otherwise possible. If you have a C++ heap, not every object in it has a vtable. Is that a good thing? Well, it depends, like everything else in software. It could be a good idea because if you have a lot of objects that don't need a vtable, you don't have to pay for it. That's what we would call a zero cost abstraction, which languages like C and Rust are very, very interested in. But on the other hand, if you don't have a vtable, you can't say with certainty that every object in a C++ heap has a vtable or not. You have to check each time. So there are trade-offs. I'm not sure there is a right or wrong answer here. In fact, I'm very sure there's not either a right or a wrong answer here. Anyway, so that is when we're talking about the layout and the sorts of things that we can do. The fact that we have a defined layout in the heap, which looks like this, where you have a pointer from the stack. Java reference is essentially a pointer with some additional type information. You have an object which has its header, and then you have a pointer, a reference which points into the Java heap, and then a pointer from the Java heap down into metaspace where the class definition lives. So this.
Sorry. No, I was just going to say, see, I'm only here to comment on the pictures because I just wanted to add, because I looked at this and I was like, what is a leopard object? I thought I knew Java. And then I remembered, I think this is an illustration from your book, isn't it?
It is.
Where the example that runs through involves leopards and other large cats. And so that's why it's a leopard object. That's not like a fundamental feature of the JVM.
No, I don't believe that you can import java.animals.leopard. It would be cool if you could.
Which is a shame. Yeah, totally.
You can write the jet, Polly. I'll back it up.
Yeah.
So what's going on here is we're just showing the headers. I think it's always nice to see them and to show that every Java object in the heap you have a header. So we've got a leopard from our domain model, and then it points into the metaspace. And this goes to show that the metaspace is a separate area from the heap. And that's because the things which are in there, I refer to them as a class heap, they are not actually Java objects. Because every Java object lives within the Java heap. So by definition, if they're not in the Java heap, they're not a Java object. Very early versions of Java, like 7 and below, they did try to squish those two together, but it didn't really work. And then you had a garbage collector that was trying to collect things that weren't Java objects, and it was all a horrible mess. So separating it out makes sense. It's also, while we're here, you can also spot that the class objects like string.class or leopard.class in this case, they live within the Java heap. So they are not actually the same thing as the class heaps. They're very closely related. They reflect one another, and I'm using that word very deliberately there, but they're not the same thing. Okay, they're effectively the JVM's own internal data structures for handling class metadata. So now we're starting to build up a picture of what we've got here. Let's look ahead a bit and start thinking about how we would build a whole Java app. So this is what we've been talking about up to now. This is some of the process. We get our Bootstrap JVM. We've got an app which we load from disk. So the JVM starts up. It allocates the Java heap. It processes the startup parameters. It probes the CPU and the operating environment to see what it's got, chooses a garbage collector, determines what set of JIT compiler intrinsics it's allowed to use, does all that good stuff that we always do at startup. It finds the app on disk and loads it up, and then starts executing. So we're starting to warm up. We get into a steady state, and then we shut down. Okay. one thing I also want to mention here is that there is the possibility during the warm-up of a second phase of class loading. So in something like a very traditional Spring setup, what happens is you load the base of your Java app. So the part which says app here, well, that's actually going to be the Spring framework that boots and starts up there. Your own classes actually get loaded when Spring builds the dependency graph for your app and then brings that in. So what that means is there's actually kind of like a double step function, because as the warm up time comes in, the number of classes loaded is JDK, application, and then with Spring it would be another one where because the middle bump would actually be the Spring framework classes. That can, under some circumstances, cause problems with JIT compilation, because what can happen is you JIT compile a whole bunch of the framework classes because they're getting called so much, and then actually once the application has started, you never use any of those framework loading classes again. So you've got a bunch of stuff which is in your compiled classes cache, which you're just not using. So that it's rare. It's only sometimes a problem, but I have encountered things where you've ended up with applications where the stuff you actually care about can't get JIT compiled because the cache is too small and it's full of Spring. It does happen. So that's fine, but maybe we should try reimagining this a bit. What can we do that's different? What happens if we what can we do to make applications load faster and avoid some of these costs, especially in short-lived environments like AWS Lambdas?
Yeah, I was going to say, if only there was some other framework.
Absolutely. So this is at a high level some of what the rethinking I think looks like. Because the other major trend that's happened to us is cloud. And in the old days, we used to have big metal servers. Oh God, I remember what that was like. We would do things like, I'd come into the office, I'd sit down with my boss every 6 months, and we'd get coffee and we'd sit there and we would plan out how many servers, and I mean physical servers, to be delivered to a data center and put into racks, we would need for the next 12 months of our project. Can you imagine that? Having to tell people how many servers you need based on 12 months. Yeah. Of course, it was an absolute nonsense. There was no way you could do it. So people used to over provision QA, do all sorts of tricks, buy more than they needed. All of that capital expenditure, was just in some cases sat around, and it was a feast or famine.
Such a waste.
Such a waste.
Buy it now in fear that you won't get the budget again next year, so you order extra stuff now.
Totally. So when cloud comes in, and I think one of the ways that I like to think about cloud is that it transforms compute from a capital expense to an operational expense. Yeah, that's a way which has got nothing to do with computers themselves or technology, but it shows you how the model has evolved, I think. And so now what do we do? Well, we have the livestock, not pets model. Instead of having these precious few servers that we look after and we lovingly rear by hand and upgrade and put them through their patches, and then we upgrade our application and put a new version on top, right? We don't do any of that anymore. Instead, we have containers, and they are very much livestock. Oh, this one looks a bit sickly. I know. Should we shoot it in the head and get another one? And that's what we do. So if that's the case, then it changes the model for how we want to do this. We have our app, sure, we build our app as a jar or a bundle or something. But now, instead of the app being the thing that gets deployed, it's the container that gets deployed. So actually producing the app and building the container are a step in their own right. Now, this requires things which are currently outside of the main Java view of the world, because we're kind of running ahead of where Java itself is going. But trying to bridge the gap between the cloud world and the Java world, I think, leads fairly inevitably to this, where we have a container that gets built, and then we can do what we want with the container after that. For the native mode, obviously that's done using Graal, and I always think Graal is interesting. I think it represents this sort of fun piece of computer science, because people always get hung up on this distinction between JIT versus AOT compilation. And the Graal compiler, which is used by GraalVM, I think shows how you can kind of straddle both sides of the divide. It's a compiler, so it takes in, at one level, a set of bytes, an array of bytes, and it gives you back an array of bytes. If you just strip all of the context away from it, that is what a JIT compiler does, and it's what an AOT compiler does. You take an intermediate representation and you turn it into machine code. But this has the advantage, if you just divorce all the context from it, that then you can say things like, okay, so I've got a method which is implemented in Java, which takes in a byte array and returns a byte array. Okay. Wow. So what? Okay. Well, I'm going to use a Java source code compiler. I'm going to use Javac, and I'm going to turn that into a class file, which I read as a byte array. And now I have a byte array to put into my method running on a Java interpreter, which takes in a byte array and returns a byte array. The byte array that comes out is guaranteed to have the same semantics as the one that went in. So I've essentially bootstrapped my own compiler. And that insight, which is at the heart of how Graal works, I think is fantastic. Now, of course, in production settings, we don't really do that, because we would want to pre-ship a compiled binary version of the compiler itself, just for performance reasons. But the fact that we can do it, again, is another indication of just how the sort of execution model is evolving. We want to be shipping immutable artifacts, and now we have a new take on how our compilers work. Are they JIT compilers? Are they AOT compilers? Well, they're kind of both, and we can use that to compile first the compilers themselves, and then the programs that go with them. So that's, I think, where we are right now in terms of the sort of state of the art for deployment. And this, I think, comes back to the question we had earlier about crack. Because what Quarkus does is to do as much as possible at build time. By shifting everything left, we're going to pull things into the realm of what we can do before the container is actually sent anywhere. Now, some of the challenges that we see with things like crack are the same, because database connections, anything which involves a network, how do you freeze dry that and put that into a container? It's not necessarily that easy, especially because, as I think the crack people are discovering, some of the things which are present at operating system level are deliberately designed, or, well, maybe not deliberately, but they're designed in such a way that it makes it actually very difficult to reliably freeze a process. There's all sorts of stuff like address-based randomization, other things to do with preventing attacks by preventing predictability, which means that it's hard to rehydrate a process without running foul of those mechanisms. I think that because Quarkus operates not quite at the process level, but slightly above that, what do you think, Holly? I think that gives us a somewhat easier time of it.
Yeah, I think so. Like, and we try and be really sort of careful and safe in terms of, because we are that level above and we're integrated into the libraries, we can look at the libraries and say, okay, well, what in the library needs to be deferred as late as possible and needs to be done at runtime, and what of this is actually going to be the same no matter what.
And of course, tricks like injection of proxies. So we say, you know, this isn't actually a network connection; it's a thing that will be a network connection. So all of those. Can can I describe that as a monadic technique? It's kind of using a monad to hold. It's a container type. It may not be fully a monad, but it's pretty close.
Yeah, I never thought of it that way, but yeah, I think that's fair.
Well, I mean, because it's a supplier or a future, if we put them
Yeah.
into Java terms rather than anything else. Yeah, so I think at this point, I mean, if we look at the corresponding, oh, that's a terrible picture at this resolution. Oh, that's terrible. I need a better picture than this. I think actually I got this one from the Oracle website, so I'm going to blame Oracle for this. Just kidding. So this is basically the way that the Graal stack works. So we now have the Graal compiler versus the hotspot VM in here, and so basically when we're producing these, if you decide to go native mode, you bring in things like Substrate, which is a very limited VM, but it has like a garbage collector and stuff installed in it, which people sometimes get surprised at. They don't seem to realize that actually it's not just native compiled Java which does that. In some ways, the Substrate capabilities are not that dissimilar, I would say, especially these days with virtual threads, from those provided by the Go runtime. People always describe Go as a compiled language, and I'm always a little bit sort of slightly not skeptical, but I'm not always 100% comfortable with that classification, because it does still have a runtime. It's not like Rust, which has essentially no runtime whatsoever when everything is kind of compiled away. But yeah, I don't know. Is that a fair comparison? Native compiled Java versus compiled Go? I think it might be.
I think so, yeah. And in terms of the performance characteristics, they're sort of getting quite comparable as well.
From which side? You mean Go?
Well, I would say, I mean, what I was imagining was both throughput and memory footprint and startup time and that kind of thing. Because at least in some cases, anecdotally, Go will have a worse throughput than Java, probably partly because of the lack of JIT and that kind of thing. And definitely when we go to native, we see that worse throughput. But then as well for that, the kind of circumstance under which you'd want to use native is when you're so sensitive to your footprint, your memory footprint, and your startup time, and there, the charts look kind of comparable when you compare to Go.
Yeah, I mean, of course, any type of performance analysis is incredibly difficult to do. I don't. One of the things that I have not been, well, I've been helping a bit, but mostly just guiding and helping analyze the results. Is we just finished doing some profiling of OpenTelemetry in Quarkus and in a couple of other cases as well, and it's just so difficult to get actual, accurate, and reliable numbers for any framework, because it's just so enmeshed in it that you have all the variables of what does the workload look like and under how much stress and what size of machine are we talking about and what's the test setup, that the number of variables just explodes. So trying to get to any kind of general statements is difficult. So
that sounds a little familiar to what you and I are working on right now,
huh? Yeah, completely.
What are you guys working on? Can you share?
Yeah, so we're working on updating some of the Quarkus performance numbers that we publish and getting a data flow for that. But then, of course, as soon as you start doing that, so that's part of it. And then the other thing we want to do is we want to make it more easy for people to run their own benchmarks as well, to just sort of say, well, I don't have a whole performance lab, but I just want to quickly do these performance comparisons, which of course people do anyway.
Yeah. Without the education around it.
Yeah, and as you say, it's very easy to end up with something like there's a sort of a spectrum of incorrect performance numbers, isn't there? And they're never going to be correct, because you are never going to have an abstraction that is actually matching to your particular problem. And so then the question is it incorrect because it's solving someone else's problem and it's a different workload? Or is it incorrect because you just measured it in a way that, so the spurious things are dominating the number that you just shouldn't even have included. And so we're trying to get a set of easy to run performance numbers that have less of the incorrectnesses, even though they will never be fully correct, because of course they can't be, and fully representative, that is.
All performance numbers are incorrect, but some are more incorrect than others.
Yeah.
Exactly.
Yeah.
And so we know people are going to do it anyway, so let's help them do it as least incorrectly as possible.
Well,
Yeah.
if you could, if one thing you might try is actually having like a form, so that if they're going to submit the performance numbers or talk about them, and to go through the form and go through the checklist, because just having that as a standard thing, what environment did you run it on? What else was running? All of it, like just a checklist of common things to help provide just the basics of an apples to apples comparison.
Yeah, I like that, because we've got like some documentation, but I'm hoping to sort of rework it as well, of like just to have that resource of, so you want to do a performance comparison. So I like that checklist.
And the other part of it too is essentially open sourcing what we do in our performance labs, so that every run becomes public and we publish the numbers publicly. In addition to the configuration and what process we went through, and all the scripts that we use are all going to be public.
Yeah, no, that's great. I mean, I think the more we can do to democratize and get this stuff out in the open, the better. I mean, but because there are still so many bad performance numbers out there, and I think it's not a problem that's ever going to correct itself, because well, we get lots of young, new, enthusiastic people coming into the profession, and they don't know what they don't know about performance and just how subtle and tricksy it can be. So you keep getting these, posts on Reddit or other forums where you just have people making, beginners' mistakes with it repeatedly. But I guess in one sense it's healthy, because it shows we have a pipeline of new enthusiastic people coming through.
Yeah. Yes. If you knew what you were doing, you wouldn't be a pipeline. But I mean, I think, it's so tricky, because I think you're exactly right, that you don't know what you don't know. And so you run a simple benchmark and you get a number out and you're like, great, I have the answer.
But what does that number actually represent?
Yep. Sure. But you have to help people towards that journey, and they have to do that journey on their own, unfortunately. Should we perhaps talk about Leiden? Because I know that we've
yes,
not running out of time yet, but we
sidetracked.
So to return to one thing that we were talking about earlier, I mentioned there were two different JIT compilers. And why is that important? Well, because even if we leave aside the difficulties of network and all the other clever things that Crack needs to do, and Quarkus needs to do to some extent, but slightly less so, we still have an issue, even if we're just talking about saving code and then reusing it on another process invocation. The hot paths through the code may change. So you can, for example, on a different day, have a different set of hot methods. And I think people would be quite surprised to learn exactly how far that goes. For example, if you restrict to the methods in the JDK and start the same process up, which is just doing regular web service stuff, by the time it gets to serving first request, the set of methods which have been JITted by the time you hit first request is not always the same. And that surprises a lot of people, because they assume that startup is, in some sense, basically deterministic. And in terms of semantics, it is, but in terms of performance, it's not. Because by definition, if the set of compiled methods is different, you're going to see slightly different performance behavior. Now, when you actually introduce to that actual changes in the way that your site is operating, the standard thing is, Amazon, when it has its big sale days, sees completely different volumes of traffic. But the shape of that traffic is often different. I used to work in futures and options when I was working in one of the banks, and we had specific days when a very specific order type would become more important than everything else, because it's the day when the contract switches over. So you need a special order type to say, okay, I need to keep this position as it is, but I need you to roll it into the next position. No other time do you see those order types at all. So if you save the JIT compilation data from that day, you have a very badly optimized system. And that's why the distinction about C1 and C2 is important, because the C1 optimizations are definitely safe. So yes, absolutely, you can save those. So now you can start to ask the question, so what can we do? Is it about saving the output of the JIT compiler? Is it about doing selective optimizations and looking at JVM startup and say, okay, well, these C1 and similar optimizations always seem to happen. So could we just ship that as a pre-compiled class library? So what they call a CDS archive. Okay, well, we can do that, and you get a small amount of benefit from that, and you can see some startup time, but it's restricted to the JDK. And now you can say, okay, well, what about the application? Okay, well, here is where it starts to get tricky, because you can do that. You can profile your application, and you can see which of your methods in your classes should also be precompiled and ready to go in a precompiled state. The problem is that's dependent on profiling. And you now have to do training runs. You have to save the archive. You have to be really sure that the archive that you're collecting from is, for want of a better word, uncontaminated by other processes. Because, oh, are we going to do this in a container? Well, what happens if the container has got noisy neighbor? It may be CPU starved. It may, all sorts of other things might be happening.
Or you shrink the amount of resources you give a container, which is what people usually do in a shared platform.
That's another issue, because the JIT compilers may well make completely different decisions based on the number of cores. So, for example, as it stands, if you run Java in a single core container and don't tell it explicitly which GC to use, you get serial. And that is probably not what you expected or what you wanted. And if you get the compiled code from that single core container, it may well not run if you then apply it to a production fleet which has more cores. In general, I don't think anyone should be running Java in a container with only one core, or for that matter, Go. Because in both cases, oh, I think we lost Solly.
That's right, I'm still here.
She may be dealing with new puppy. So
yeah, I'm not sure what happened.
She'll be back. Yeah,
maybe her computer thinks it's time to get ready for insights. back to the time zone issue.
Right. Yeah. So you can do some of that, but the complexities around the training runs and understanding your runtime environment means that this is still kind of I guess not quite a down in the weeds, but it requires a certain amount of sophistication on the part of the people that are doing the training runs. Which isn't to say that there isn't a lot of interesting work being done here. So one other example that's being worked on is Lambda expressions, which currently it's difficult to do full ahead of time compilation with certain parts of Java code because of things like invoke dynamic, which has a runtime decision about which method is actually attached to the call sign. And they're used in lambdas, for example. So that's an issue. So you need to do some work to convert those heavy dynamic pieces of the platform back into something which is more static. So kind of the overarching philosophical question here is, we have this platform from the 90s. It was wonderful. It was designed for Big Ten. It was designed to be dynamic and very open and very extensible with things like class loading and reflection, and now invoke dynamic and method handles, and it has all of this wonderful runtime stuff in it. So even though it looks like C and C++, it's actually not. It's actually very dynamic. But that dynamism comes at a cost. So as we move into the cloud world, we're building immutable containers. The world looks suddenly a lot less dynamic. Our applications, if they encounter change, will be redeployed. So has the Java needle, which is secretly swung all the way over to dynamism, do we need to work on bringing it back? Do we need to work on techniques where the dynamism is available if you need it, but if you don't, can we reduce it somehow? Can we get rid of these dynamic call sites? Do we really even need reflection? If we know all the reflection paths, could we somehow just switch off reflection and just okay, we don't need that. We've pre-computed all the reflection.
I think most of the world would break if you did that.
Well, to a certain extent, it's what we do with native compilation, right? Isn't GraalVM? You have to tell it what the reflection paths are.
Yeah.
So those are the sorts of things you can do. Are there other things as well? Could we strip down and get rid of everything that isn't is dead code from the JDK? Sure, but where is the benefit in doing that? We still don't know yet. So there are some some really good efforts out there. I mentioned it. It's called Project Leiden, which is being run by Oracle. The reason it's called Leiden, by the way, which is a town in, is it the Netherlands or is it in Germany? I can never remember. I think it's in the Netherlands, and I'm going to get lots of angry Germans in the comments, doubtless.
That's an easily Googleable answer, right?
Right, totally. So it's either in the Netherlands or it's in Germany, and it's famous because it has one of Europe's oldest universities there. And it's the Netherlands. Yay, I was right. And at the university, they came up with a thing called a Leiden jar, which basically is one of the earliest forms of electrostatics. It's kind of like what we would now call a capacitor, but it was also at one stage called a condenser. And so the idea of condensing a program, of taking its dynamism and constraining it, is at the heart of what Leiden's doing. It's still in the early stages. It has the advantage that because it's happening within OpenJDK, it's something that Quarkus can build upon. And in some ways, I think about it that Quarkus was thinking about some of these problems first, was recognizing where we were going with cloud native, and we were kind of ahead of the curve. And so now, great work is being done in OpenJDK, two-way discussion, build something which is standardized, something which is definitely Java, and then Quarkus' solutions can adapt to fit on top of it. So I see this as as really promising, really exciting, and yeah, it's amazing that this subject has, like I said at the start, it was an old subject, and it seemed to have been put to bed decades ago, and yet here we are talking about it at the end of 2025.
One of the value propositions of Leiden, which I really liked, I don't know to what extent this is actually true, but is that with native image, we sort of had this binary where you can be native or you can be JVM, and I think the GraalVM team are as well sort of working on making that a bit more of a spectrum because it's not such a helpful binary, and that's what Leiden is sort of trying to do as well, is make it a bit more of a spectrum so you can decide how much dynamism you still want and how much it's going to help your performance to get rid of that dynamism, and you can choose where you are on that slider.
Yeah, absolutely. I mean, I think it will be a while before that comes to a lot of applications because it has the same issue that we have with training runs. It's currently, that's a high sophistication thing to do. And one of the things about the Java platform is it is a fantastic general purpose runtime. I would argue that it's the best general purpose one that's out there in consumer terms. And because of that, you don't have to know a lot about it to get it to a tolerable state. In fact, it runs even when you have some horrible configuration that's been come up with by decades of, or in some cases decades, years or decades of operations teams finding useful tips on the internet. So you look at the configuration file, you're like, what is this? And yet somehow it still runs because the runtime is just that capable. So that's a disconnect. There's a disconnect between the sophistication that things like Leiden and so forth require and what we want for a mass market consumer grade, right? Because Java is a mainstream technology. That's its strength. It's also, well, lots of people don't like it, but I like building solid things with it.
So something that kind of hit me in the back of the head while you were talking, I didn't want to interrupt you when you started talking about like this needle between highly dynamic versus no dynamism. Where did, and I know this, it didn't really take off, but the whole J2ME thing that was what, from the early 2000s, was that trying to solve some of the same problems, or was it trying to just make the JDK a little bit smaller so that there was less stuff?
So J2ME really is from, not quite the dawn of time, but maybe from when saber-toothed tigers roamed the earth rather than dinosaurs.
Yeah.
But it really is to deal with the fact that the devices involved are just so constrained. So it's not actually compatible with J2SE, like what we think of as Java. It's different in some ways, like the bytecode's different. It's a related technology, but it's very much a dialect which is spoken for specific hardware limitations.
Gotcha.
Whereas Android, of course, is famously based on the Java class libraries, but actually has a different VM. So its runtime is not hotspot, and in fact is not actually remotely a Java VM.
I was going to mention Android until you brought it up, because it's a very similar thing.
Yeah, which is what's interesting about the evolution of the model with Zero and the work that's being done by Gluon and some other folks in the mobile OpenJDK project. They are bringing real OpenJDK, which is based off of mainline, and making that run on Android rather than using the Android programming runtime. So that would look like an Android native compiled binary. So like the Rust folks have got a toolchain where they can write Rust, and that will run on Android without using the Android programming runtime. And this would be the same idea, that this would be real Java applications that would run as native Android applications, which is kind of cool. The Android case is easier because they don't have the restrictions about JIT compilers, which iOS does. But the same approach on iOS will be, and Leiden's a great example, right? So because Leiden, if you can do things like, well, you can ship a CDS which contains C1 compiled code, well, that will give you a performance boost in iOS. But outside of iOS, where you can run a JIT compiler, you can imagine a circumstance where you ship a pre-compiled version of your app, but the runtime is still able to patch out the C1 compiled pieces and replace them with a faster C2 piece.
It's very cool.
It's exciting times. I mean, I think, watching what will happen in the next year or so, we've talked about execution. I mean, obviously a lot of this will also play into the other programs which are still out there, including, of course, Valhalla, which seems to be coming a little closer, but not here yet.
Yeah, I mean, and I'm just thinking as well, like going back to your question, Eric, about J2ME, that so many of these things, they just sort of go back and people had an idea 20 years ago and it never really took off, and now we're having the same idea again of like, let's do AOT. It's like, no, we've tried AOT many times. It was never a good idea, but now it is a good idea. And it's because, as you say, Ben, the technology landscape has changed. And so then there's a new requirement that wasn't there at the time. And of course, we're also just smarter.
Sure, but also the compute capability. I mean, that's one of the other things which I think is interesting about this. If we take a historical view for 1 minute, was Java far-sighted, or was it just lucky? Well, maybe you need both, right? Because things like the design of the JIT compiler, the design of Hotspot, are predicated on the assumption that computers will get faster. And it came out right in the middle of that Moore's law curve back in the late 90s, the early 2000s. But specifically with the way that the JVM works, all Java programs are multi-threaded, all of them. They may only have a single user thread, but because your code is executing inside the JVM container and as part of the Java process, the VM's threads always are present. So that means that your program will behave differently on a single core machine, assuming you can find such a thing these days, versus on one which has more cores. Because your JIT compilation threads, for example, can run at the same time as your program thread. So the performance profile was spread out over the available cores. And you can see that in things like thread pools, where you can have a different size common pool, which goes back to Eric's point about single core containers. So
yeah. I was going to say,
just,
I like you. I was in financial systems before, like way before, back in the 90s, like when Java first came around, and I remember like this. Every time new CPUs came out with it, every CPU was still single core, but you were like doubling CPU speed every single time you upgraded. And I remember we had our trading app, and we upgraded and we were running bare metal, and we upgraded our app, and we actually got slower because the hardware that they picked out, it was a faster CPU. It was like a bigger, beefier machine, but our app was more IO bound, right? So the fact that we had all this memory was great, but we didn't need it because we were doing mathematical computations, and we needed IO and we needed CPU speed. So we actually had to buy new hardware that was faster clock speed, but less resources to speed up the application. I think that goes to your point where it was the JIT was optimized for knowing that things are going to get faster in the future. But yeah.
And to your point about CPUs, I mean, this is, I love showing this graph as well, because this shows you where Java came from. So when Java started to come around in 95, and this shows you the dominance of various processor types over that time. So Java grew up in a heterogeneous world. That's why the idea of a VM as an abstraction layer and of platform-independent bytecode makes sense, because you have to deal with this.
We were running on Spark.
Yeah. Yeah, and of course, so I think it's difficult for younger folks in the profession who maybe have only grown up and only ever really known an area which was dominated by Intel, and then latterly, obviously, ARM has come to the fore as well. And actually, Intel, it's interesting to see that they're actually not doing as well. They've actually had to take out some pretty big loans lately as well, compared to where ARM is going.
It'd be interesting to see this chuck as it stops in 2016, like where
it
goes to now, because now you've got Silicon, and you've got ARM, you've got all the Snapdragon processors and all that stuff. So it's almost kind of, we had all this heterogeneous stuff, and then we got homogeneous, and now we've kind of gone the other way again.
Well, because here I've got my little tiny Raspberry Pi, and this thing is quad core, and it's just inside that there's a quad core Snapdragon. And it's just incredible that within the palm of your hand you can fit that much processing power, and of course it runs Java. So yeah, the processor story is still not over.
I think we could keep talking all day, but we should probably stop here. But yeah, thank you so much, Ben. Really, really interesting.
Yeah, well, it's great to talk as always. I hope everyone listening had a fun time, and I hope to see you again soon.
Yeah, we'll see you all next week. See you.
What time? We'll figure it out between now and then.
Just watch the website.
That's a really good point. And actually, I think next week I'm switching chairs. And I'm going to do a whole bunch of demos. And because it's a whole bunch of demos, it is a little bit challenging and does need a bit of prep time. So I think I probably need to figure out what time we're doing it. So that
Eric, did your clocks change this Sunday?
They changed yesterday.
No, I've asked it. Eric's.
No, not.
Oh, sorry. I thought you were talking to me. Sorry.
That's a good
question.
I think is it 2 weeks?
I think it's in 2 weeks. November. Actually, no, it is this week, November 2nd.
Oh, okay. So it'll be the same no matter what.
So it'll catch up. So it's the spring where we're off by several weeks. It's the fall when it's only 1 week.
So it is just a single broken week, and so it's actually back to normal. This was just a weird one.
Yeah.
Yeah. Okay. Yeah. So no worries for anybody next week. It will be at the predictable time, whatever that predictable time is in your time zone, and we will see you all next week. See you.
Thanks, everyone. Bye.